Topic introduces the distinction between linear and nonlinear derivatives and explains their importance in financial risk management. Linear derivatives, such as forwards, futures, and swaps, have payoffs that change proportionally with movements in the underlying asset. Their values respond directly and predictably to market price changes, making risk measurement relatively straightforward. Nonlinear derivatives, including options and structured products, exhibit asymmetric payoffs because their values depend on more complex relationships with underlying variables. These instruments contain embedded optionality, causing sensitivity to market changes to vary over time. Understanding the behavior of both derivative categories is essential because financial institutions rely heavily on them for hedging, speculation, and portfolio risk management. The topic explains that linear derivatives are often easier to value because their payoffs can usually be determined through direct pricing relationships. Futures and forwards derive value from expected future prices of underlying assets, while swaps exchange streams of cash flows based on interest rates, currencies, or commodities. In contrast, nonlinear derivatives require more sophisticated valuation techniques because their prices depend on volatility, time decay, and probability distributions. Options are particularly sensitive to changing market conditions through risk measures known as Greeks, including delta, gamma, vega, theta, and rho. These sensitivities help risk managers estimate how option values respond to movements in prices, volatility, interest rates, and time. The topic further emphasizes the challenges nonlinear derivatives create for portfolio risk management. While linear instruments generally exhibit stable relationships with underlying market factors, options can experience rapidly changing exposures during volatile periods. Gamma risk, for example, reflects how delta changes as market prices move, causing hedging requirements to shift dynamically. Financial institutions holding large options portfolios must continuously rebalance positions to maintain effective hedges. Moreover, nonlinear payoffs can amplify losses during market stress because risk exposures become highly sensitive near strike prices or expiration dates. As a result, institutions use advanced pricing models and simulation techniques to capture the complex interactions between market variables and derivative values accurately. Topic also examines Monte Carlo simulation, stress testing, and scenario analysis as critical tools for measuring portfolio risk under uncertainty. Monte Carlo simulation generates thousands of potential future market outcomes by randomly sampling from assumed probability distributions. This approach is especially useful for portfolios containing nonlinear derivatives because analytical solutions may not exist for complex instruments. By modeling numerous market scenarios, risk managers can estimate distributions of future portfolio values and calculate measures such as value at risk and expected shortfall. Monte Carlo methods are flexible because they can incorporate changing volatilities, correlations, and multiple risk factors simultaneously, making them widely used in modern financial institutions. Stress testing and scenario analysis complement quantitative models by evaluating portfolio performance under extreme but plausible market conditions. Stress testing typically examines the impact of severe shocks, such as interest rate spikes, stock market crashes, or liquidity disruptions. Scenario analysis considers broader economic or geopolitical events that could influence multiple market variables simultaneously. These approaches address weaknesses in statistical risk models, which often underestimate rare but catastrophic events. Financial crises demonstrated that historical relationships between assets can break down unexpectedly, causing large losses that traditional models fail to predict. Regulators therefore require institutions to conduct regular stress testing to ensure resilience under adverse conditions and maintain adequate capital buffers. The topic concludes by emphasizing the importance of integrating derivative modeling with comprehensive risk assessment frameworks. Monte Carlo simulation provides detailed probabilistic analysis, while stress testing and scenario analysis introduce forward-looking perspectives on potential vulnerabilities. Together, these tools help institutions identify hidden concentrations of risk and understand how portfolios behave during periods of extreme uncertainty. Linear and nonlinear derivatives require different modeling approaches because their payoff structures respond differently to market movements. Effective risk management therefore combines statistical modeling, economic judgment, and ongoing monitoring of market conditions. By integrating simulations with stress scenarios, financial institutions improve decision-making, strengthen regulatory compliance, and enhance their ability to withstand unexpected financial disruptions.